According to your textbook, a buffer solution is a solution of a weak acid or a weak base and its. Now these combinations look like acetic acid and sodium acetate, or a weak base like ammonia and ammonium chloride as the salt. So you can see that it's got to have both one of our main weak acids or weak bases and something called a salt. That's really just the ion version of our core part of our acid or base with a counter ion that's not going to participate in the reaction, like sodium ions or chloride ions. Now, what's really interesting about buffer solutions is what they can do. They have this natural ability to resist changes in pH. And some textbooks don't exactly explain why that works so well. So let's take a look at it here. If we add some strong acid like HCl to any kind of solution in water, this sucker completely dissolves and dissociates into H plus and Cl minus ions. We can ignore the chloride because it's not going to react with pretty much anything. And we're going to focus just on what H pluses will do when they're added to a solution. Okay, so let's consider our two buffers from before. Let's say we have CH3COOH, our acetic acid, and acetates floating around in solution. Okay, so if I add in my H pluses into this beaker, think about what kind of chemical these guys will hit. If you're thinking that pluses are going to be attracted to minus things, then you have the right idea. The acid is going to remove some of the weak base from solution. Which consequently makes more of our weak acid. In our next video, we'll talk about how to calculate the changes using stoichiometry in these two species, because that's seriously going to affect what goes in your ice table. Okay, so let's talk about our other buffer. Let's say we have our situation where we had ammonia and ammonium ions in our buffer. If we add H pluses to this solution, our H plus is not going to connect to our ion this time because those are both positive charges. It's going to be much more attracted to the weak base, which in this case is ammonia. So we would write our reaction for this as H plus NH3 makes the ammonium ion. Again, this is going to increase our concentration of our weak acid and decrease the weak base before you start equilibrium concentrations. Okay, now let's consider what happens when we add a strong base to both of our buffer solutions. In our first buffer, we have our acetic acid and our acetate ions. If I add in a bunch of hydroxides from a strong base source like sodium hydroxide or potassium hydroxide, I would see that my negatives aren't going to be attracted to each other. So our hydroxide will actually attack our weak acid and steal a hydrogen from it like this. CH3COOH plus an OH minus. This is going to yield water and our acetate ion, effectively decreasing our weak acid concentration and increasing our weak base concentration. Now if we add our strong base into our solution with the ammonia and ammonium ions, then we can see something very similar happens. Our hydroxide is going to be attracted to our weak acid. That weak acid is going to donate a proton to the hydroxide, forming the weak base and water. So it's very important to practice writing the initial stoichiometry reactions that are going to be happening in these beakers. After we see what happens with this first step, we can calculate the equilibrium concentrations of all the species, and more importantly, the pH.